So hello everyone. You may have come from the announcement tweet from my colleague Hao Junzhao on Picotron. While Picotron is a very readable and concise code base, it may require some domain expertise to understand what is going on, like how tensor-parallel works, how data parallel works, how pipeline parallel works, and so on. And that's why this video tutorial is here to help you go through all these details. So it will be a mix of whiteboard and live coding in a way, such that at the end you will be able to implement Picotron from scratch and understand the thought process that we went through in order to build this framework. So at the end it holds in 8 files, basically Picotron, but refactor so that it fits this video tutorial. And you see it's decomposed in step 1, 2, 3. So in every step, there will be like a diff file showing what is the most important changes in the steps. For example, if I go on to tensor-parallel, we see that only some changes related to tensor-parallel will be displayed. And okay, that's I think a good way to guide the viewer on the thought process of the framework. So for this video, we are going to only talk about the step 1, 2, and 3, so modeling, process group manager, and Dataloader. So let's talk about the modeling. So which kind of things we want to parallelize distributed over GPUs. We are going to use a transformer model, more precisely a llama model. If you are not used to the llama model, I think there is a thousands of videos or blog posts explaining the inner details of the architecture. But for us, we're only interested in the blocks in general, so that we know on which dimension we are applying the distributed technique. So let's start a bit with the modeling. So we have the input here, okay? Oh, why? It's so badly written. Pardon me for my writing skills. Didn't touch a pen since school. And here we have after that the embedding layer. Okay. And oops. And after the embedding layer, you have a decoder. Okay. This is where all the attention MLP thing is happening. That's the core thing. It's usually repeated n times. We don't know how many times, depends on the model. And then you have usually a final norm. Okay, this is a RMS norm. Then you have like a final proj. Okay, and I will reduce a bit. And after that, you have the logits. Okay, the actual logits. Okay, cool. So this is your llama. And now we can start I think we can add as well before the dimension of the model. So the input is batch size, sequence length, okay? Then after that you do batch size, sec length, and you have hidden size, okay? Hidden, okay? This is the same thing for the decoder. Even after the n successive call. It's same thing for the final norm and final proj. We should resize them a bit. Okay. And at the end, you have the logits, which are batch size, sec length, and vocab size. Because you have to project back to the embedding. I mean, to the embedding space. Okay, that's good. So now, what are the 3 different type of parallelism that are commonly used? 3 types. The first type is pipeline parallel. Parallel. So this is a way to split the model vertically or model layer wise. Model layer dimension. For example, it can be, let's say, this way, okay? It's very not correct in terms of implementation because actually you have on one GPU the embedding and decoder and all the decoder, and on the other GPU the final norm and final project. It's so uneven, but in general, you want it to be evenly splitted across GPU so that the workload is well splitted, okay? But just for the concept, here in theory, we say that it's possible. So here we have two GPUs, we split the model into two, okay? Now the second form of parallelism is tensor. Here it acts on the hidden dimension, hidden size dimension. So what does it mean when I say that? It means that it's acting intra-layer, within a layer. For example, when you have an embedding, or a weight, you split into two if you have two GPUs. One shard will belongs to a GPU and another shard will belongs to another GPU. So if I had to draw with a line how it will look like this way. A straight horizontal line, okay? So I will do this way, 0, indexing, so big, up, and 1, no, maybe the other way around. This for GPU 0, GPU 1, okay? And now that we have discussed the 2, 1, we are missing an important one and the most common one, the data parallel, which act on the batch size dimension. So what does it mean when I say batch size dimension? Actually, what it means is we are trying to consume more data, which means that we can feed more data we want our model to work on more data, more batches. But the issue is, since it's on the single GPU, you can only feed sequential batches. Because when you give one, it has to do compute, and you have to wait that it finish to process the batch before getting the other batch. So what you can actually do, a simple way, is just replicate the model on another GPU, okay? Like this. And this way, you can just replicate the model and feed more batches to the different replica. So if you have two replicas, you can consume 2 times faster your data loader. Up and up. Well, so that's what it means when I say data parallel is applied on the batch size dimension. So here, if we have to count the number of GPUs we have 8 actually, if we apply the 3D parallelism techniques. And we see as well, so we have PP equal to, DP equal to, and TP equal to, and it's a total of 2 times 2 times 2, 8 GPUs, okay, involved. And you see that they all act on different dimension, which means that they can be used together. That's why we are talking about 3D parallelism, because they are independent. Okay, so now that we understand conceptually on which dimension we can apply the parallelism technique on our transformer model, we can start to look a bit at the code. So we have a model file here for a llama. As you have seen, it's the same as the one I said. There's the same building blocks. You have the input ideas, embedding, a certain number of decoder layers, a final norm, and then you have like the final proc that produce the logits. We can take a bit of the look at the decoder layer. It's essentially the attention layer and MLP. So when we split intra-layer, what we actually mean splitting intra-layer the decoder, or applying tensor-parallel on the decoder layer, is actually splitting the MLP and the attention part, okay, into two shards if you have 2 GPUs. Then the transcript looks like this. There's a lot of this is argparse just to get some argument in the command line. We have this distributed setup here. We call actually dist init process group. If you happen to do distributed training, you cannot launch a script without calling this PyTorch function, because this will enable you to set up all the ranks and word size and use the torch-run command. But we will talk about this in the next steps, okay? Just take it for granted for now. And then we have the model initialization. If you happen to want to have a smaller model, you can just overwrite the attributes with the command line arguments. Then you can create the llama, you train, and then you can call the optimizer here. And after that, you have a simple training loop. Pretty much it's not a training loop, but it's like we create dummy data, 0 grad, forward pass, compute loss backward, optimizer step, and then we print the loss, and we don't forget to destroy the process group. That we don't know what is for now, but it's okay. So it's pretty standard PyTorch code. And if we happen to run the code, you have to run it this way, torch run and proc per node equal 1, which essentially means that you are going to use 1 GPU to run the script, proc per node. And let's see what it's producing. So it's printing 11. Okay, why not? So now we can start to work to go on the second step. So what are the new changes in the second step? So first I will just change the directory to avoid any issue if we happen to run the code. Okay. So we have seen that there's a new file called process group manager. Okay. You have a class, a function. Then we have a train script with a call with ondb, 2 import of the function, some new arguments, a new call next to this index process group, some 1db utils, same thing here. The way we print is a bit different now. We call somehow a global rank. We don't know what it is now. And then we have like the 1db here, just 1db stuff. Okay, perfect. So how does it look like, the process group manager, and what it is for? So it looks like this. But I think it's better that we go to the whiteboard to discuss a bit about the use of a process group. So let's go back. So we said we had to discuss about what is process group manager. So what is this? So okay, so let's first index the thing, because since we have 8 GPUs, let's index the whole thing. So let's say this one is GPU 0, okay, and this one is GPU 1. This one, oh wait, let me just write GPU 1. This one is GPU 2, GPU 3. Actually, this one is GPU 4. This one is GPU 5, 6, GPU 7. Actually, just this is not correct. It should be 0 and 1. Let's go. That's okay. It's just a small typo. Okay, it's just the rank of the PP was not correct, but just I used the wrong indexing. But okay. So now we have the same schema as before, but we add on top the corresponding GPUs. So you see here that, for example, if we were only focusing on tensor-parallel, so the two reds here, we see that since only the GPU 0 will communicate with the GPU 1. Why? Because the embedding layer, for example, is sharded between the GPU 0 and GPU 1. Okay? So which means that GPU 0 is not going to communicate with GPU 2 because they don't have anything in common. Okay? Same for pipeline parallel. If I happen to choose, for example, GPU 1, you see that it's not going to communicate with GPU 4, for example, because they hold the same number of layers, but more importantly, they are not in the same replica. Okay, so you see, GPU1 is only going to communicate with GPU3 because it has the whole layer here, and GPU3 has the other part. Okay, and for data parallel, it's a bit different because since we are replicas, uh, we uh, we actually have to find the corresponding GPUs. The corresponding location for GPU 0 will be GPU 4 because they have the same spot. GPU 3, for example, GPU 3 will be GPU 7. Okay, so now we start to understand. Oh God, it's so okay. So now we start to understand what it means, the process group manager, because the goal of the process group manager is go from raw GPUs ideas. So we have like 8 GPUs, so it's indexed from 0 to 7, from GPU ideas to a subset of GPUs that fits your parallelism schema. For example, if I do tensor-parallel, I only want a subset of GPUs that will make sense in the tensor-parallel context. So only these two, a list of this one, for example, and not this one for TP. It makes no sense. That's why. And yes, so we can start to take a look at the process group manager. So this one is the assert. I mean, there's an assert, but okay. What is this? So this one is the global rank. So the global rank is the actual IDs of the GPUs. So if you have 8 GPUs per in a node, so a node is generally 8 GPUs. Sometimes it can be 4, it depends. But here in this case, if you have 8 GPUs, it'll be indexed from 0 to 7. The word size is the total number of GPUs involved, and the local rank, well, in our case, since it's in a single node, it will be the same as the global rank. But suppose you have two nodes, 16 GPUs, the global rank will range from 0 to 15, but the local rank will go from 0 to 7 for a single node, and the other node will be 0 to 7. Okay, so now we can take a look at the grid. So yeah, the grid looks like this. So what it is essentially the thing that we have drawn. So we can check in the code. So I will fire the debugger. Yes, this command. So basically, instead of running torch run, I trigger the debugger through the command line. I think it's just a style of doing the thing. I prefer triggering the debugger through the command line for various reasons. The first one is so usually how people does it is going to launch JSON here in VS Code and writing the whole command of debugging inside. So every time they have to edit something like the DP size or PP size, they have to edit the file. In my case, I can just use the CLI. And it's as well more convenient when you use it with Slurm, which is a software to submit your job to a cluster of GPUs. And this way I can submit with in the CLI the debug py, and I can choose to trigger or not the run because it's listening to a port here, like 5, 6, 7, 8, and here I input the port 5, 6, 7, 8, so it will only trigger if I run this button here. It's cool for debugging through Slurm, basically, if you happen to do that. So let's print. So what's happening here? So we have like here 1, 2, 3, 4, 5, 6, 7, 8 process that has spawned, which is pretty much the number of GPUs that we have. If we happen to take this one and print the global rank, it's 1. Okay, it's not necessarily ordered, no? Okay. So this one, what is this number? Is 0, and if I take the last one, maybe it's 7, I don't know. Okay, it's 7. So we have all the rank. So let's go back to 0, okay? The rank 0. Now what we are going to do is to print the grid because we wanted to see what's the grid. So the grid is this way, okay? is just a grid with pretty much representing our GPUs here. And now what I want to do is to find the different subgroup. So here, I cannot print TP group like this because it will just output an object. I cannot either, I can as well print the group ideas, which is what we are interested in, but they are not convenient if I show it this way because it only show the for occurrence rank, what is the subset that it communicate with. What I want is just the global list, so it's easier. So this way I will just print this part here. And so what is this this line of code doing? It is taking the grid, iterating over the grid with the data parent P and pipeline parallel, and just keeping the tensor parallel one. So I will take this, up, copy paste, call TP here. Up, there is like extra parentheses, I can remove and print TP. So you see that here you have a subgroup of 0 and 1, 2 and 3, 4 and 5, 6, 7. If we check with the whiteboard, we see that indeed in context of tensor parallel, 0 and 1 is communicating together, 2 and 3 together, 4 and 5 together, and 6 and 7 together. Okay? And so if I happen to print as well the PP group, so here, up, 0 and 2, indeed, 0 and 2. Then we have 1 and 3, and 3. Then we have 4 and 6, and then the last one, 5 and 7. So it's indeed correct. And now for DP, the last one, before we move on. Because I forget up. So you see DP is 0 and this corresponding position 4, okay? 0, 4. Then you have 1 and 5, 1 and 5, oops, 1 and 5, 2 and 6, and 3 and 7. 2, 6, 3, 7. Okay, makes sense. Okay, it's correct. And yeah, so that's cool. And so what can we talk about more here? Yeah, the tensor. Okay, so here in the bottom you just have like some utils. For example, if you want to within the TP group ideas to get the first rank or the last rank. Same for pipeline parallel. Here, word size, first rank, last rank, some utils like is first stage, last stage of the pipeline, what is the next rank, what is the prev rank, okay? And same for data parallel. Data parallel, which is here. Data parallel, get word size, deep group ideas to get the first rank, last rank. Okay, so now we can discuss a bit about the process group that we have left earlier. So now that we know what is the global rank, this init process group is a parameter function that will enable you to actually specify the characteristic of your distributed training run. You have the global rank to input, the rank, sorry, in our case global rank. Then you have the word size for the number of GPUs, the backend. The backend is during distributed training, you will call a lot of functions specific to distributed settings, like all reduce, all gather, broadcast. Those are implemented in different backend. The most known one is NCCL. It's NVIDIA Collective Communication or Communication Collective or something like this. And yeah, it's the main one if you want to use NVIDIA GPUs. If you want to run on CPU, it's called glue backend. It's the same primitive, but for CPUs. Here, it's the init method. It's calling env and // So basically, it's the method used for, if I remember correctly, how your GPUs will discover each other. And normally, it should be return something like master address here and master port here. but in the doc it can be left untouched because it will automatically set it. But if you do for multi-node, more than node, you have to specify some stuff, okay? And then you have the timeout. Some collective communication such as all reduce takes time, and sometimes it can hang if you have a lot of GPUs. And it's good to set up a timeout in case it hangs forever. So here I set it to 2 minutes. If after 2 minutes it's not producing the result I want, it's just hanging, I can automatically kill the process. And then you have this setup group manager that is actually creating a global process group manager. I think it's fair to do it this way, to have a global process group manager, even if people can argue with against the global thing, because if you modify something, you don't know where it has been modified. But I think in the context of global process group manager, since you instantiate it and just read through it and never create attributes inside, I think it's fair. We are not changing the state of the process group manager at the end. So it's just in it and that's it. And we can call it in every function, every file, just going this way. And we can do pgm, the process group manager, global ring. Okay. Okay. So I can kill all the things, make sure everything is killed. Okay. Now that we have talked about the process group manager, I think we can move on the last step, the data loader. So let's see what are the different changes, So we see a new file called Dataloader, okay, that we can skip, and then we have like new variables that comes into play. Micro batch size, gradient accumulation, sec length, we know about it, max token, okay. We have a new trend step that pretty much look like more like a real training step. We have some arguments, the call to microbatch data loader, some real training loop here. So you see we loop over the number of tokens, and we actually do some stuff. Optimizer 0 grad, trend step, optimizer step, some printing, and 1 dB. Okay, good. Okay, so it's seen. Okay, so yeah, this is the training loop I've seen in the patch diff. We can take a look at the trend step actually. The trend step is here. And we see something with grad arc step and okay, so what it is. So let's just go back to the whiteboard and think about it a bit. So if you work with LLMs, you may have heard about the word global batch size, okay? Global batch size. Most of the time, it can be like 32 or something, okay? But the thing is, sometimes your global batch size doesn't fit into memory and you get this famous error OOM, out of memory. So since you cannot fit your batch, you cannot feed your model with this batch size, 32. Actually, batch size here, remember, it means that we want 32 samples. Well, you have to be a bit clever on emulate a batch size of 32, and this is done through having a smaller batch size and compensating with the grad accumulation. Okay. So in our case here, if we wanted to do 32, we can do micro batch size of 4, and then grad arc it is equal to 8. So what does it mean? If you look at the code here, you see that the grad arc step is just our way to iterate over the data loader 8 times. So here we are fetching 4 samples at the first iteration. Second iteration, we fetch again 4 samples. So after 8 iterations, we fetch 8 times 4 batches. So 32. And we accumulate so basically we accumulate the gradient and we compute the gradient only after the grad at step has been finished. So that's just a smarter way to avoid to bypass this out of memory error by splitting into two things. Okay, and there's some details that I omit. Actually, there's another variable that comes into play is in this formula is the DP size. Here it's equal to 1 because we didn't implement that DP yet. So it's equal to 1. But if you have data parallel and you want to consume more data, since you have replicas, you must indeed multiply this thing by the number of replicas you have. That's why the DP is taking into account in this formula. Okay. And sometimes you see a very large batch size, like 496, okay? It's because they include as well the token, the sequence. I call it global batch size sequence. So basically, it's just global batch size times the sequence. Okay. For example, here we will run the code with I don't know. I have command here. Okay, on one GPU, you see micro batch size 4, grad accumulations 8, sequence 128. We want to iterate over 40k 960 tokens. Okay, so here if we multiply everything here and get the total global batch size, so it's 32 times the sequence, which is 128. What's the okay? So it's 4k96 tokens. Okay, so this is the global batch size with sequence length. And you see that if I run this command, I want to iterate over max token 40k960, which means that I will do this divided by 4k96, which is 10 steps. So let's verify if it's indeed doing that. I don't want to run you on 1db. Yeah, whatever. Maybe just wait a bit. Okay, it's because I'm still in the step 2, I need to go to step 3. Okay, hop là. Okay, it's not going to call 1db, but whatever. So we have to verify that it's indeed doing 10 steps, each step consuming 4k96 token per step, and yes, and seeing if the loss is going down. So the loss is indeed going down. You have like the maximum token here, and you see that it's going down 4k96 token every time, increasing until the step 10, where it has fulfilled all the token. And the loss is smaller than at the previous steps. So far all good, and you understand the data loader. We'll go through a bit on the code of the data loader. It's a very naive one. I don't think it's very suited to distributed training, but at least it works. There's, I guess, countless of optimization that we can do. And since we don't even have data parallel at this stage yet, we didn't add any distributed logic to it. So it's very bare, the normal data loader. But it's worth going through it because why not? So you see that we set a bunch of attributes here, and we call the tokenizer, and we load the whole data set, even if we don't need it, everything, but there's some optimization that we can do. You see that we call tokenized dataset here. So what is tokenized dataset doing? So this is a function that will take into input your dataset and apply a map function. So it will, over your dataset, apply some sort of function called tokenizer func, which is a partial function that take into input this function, tokenize group text. And you have to understand at this stage that the dataset is just like a list of strings, okay? So what we are trying to do here is to First, encode your string of your list of strings into a list of tokens through this function here. Then you concat every list of tokens into a single list of token. And once you have done that, you split your list of tokens into batches of tokens of size sequence. That's the last part. Okay, and some important function that is important to know in the micro batch data loader is the collate batch. You probably have heard about this function. Its goal is to actually create the input and target ideas. Sometimes you can create the attention mask if you want. And remember that when you in LLM training, more precisely in autoregressive settings, you have to shift a bit your labels to force the training. And I think that's it for this first video. I'm very sorry about this small cut that I had with my whiteboard. Hopefully I will fix that in next iteration. Thank you very much for listening and have a good day.